There are two announcements or two due dates and two talks this week. Let's get them one at a time. Homework 4 is due today. I hope it started. Hope you're done. Are there any questions about homework 4? Or any concerns about it? So just so that I get a sense of how you all feel about it, Do you feel like homework 4 is easier than the rest of the stuff, or is it more work?
It's easier.
It's easier? Okay. Yeah?
It definitely took a lot more interpretation than I like what the lessons did, and you kind of clarified that by saying it's just like as long as we stated our assumptions and then kind of ran with it. I guess we'll have to wait till we can get our grades back to like really see how well we.
Sure. That's a different thing. But
yeah, I just felt like it took a little bit longer to like make sure that we weren't missing anything.
Okay.
For the subtleties of the wording and like that.
Were the proof parts of it difficult or easy? Just little, nod of heads or something. Easy? Anyone say easy? Okay. So the reason I ask is homework 5 is going to be, in some sense, an exact opposite of homework 4. Not in terms of easiness or not, but it's going to have very little theory and mostly implementation. The pendulum swings the other way this time. We're going to have, you will be implementing a whole bunch of things that we've seen and we've not had the time to actually have, or you've not had any opportunity to implement stuff. In particular, it will involve SAMs. And I'm still thinking if I should include some sort of ensembles or trees or not. I will take, I'll decide soon. And the idea will be that you compare a whole bunch of learning algorithms on some small data set. And you can, the good news about the homework is once you implement that, you'll have a lot of things for your projects as well. So that should be helpful. Speaking of projects, there's a deadline for projects on Thursday. I think this is Thursday, right? Yeah. You need to submit your intermediate status report. I know that some of you have already done that on Canvas. The rest of you have on Thursday. And you know what to do there. Are there any questions? I am almost certain that I have responded to everyone who has who's working on exploratory project. Is there any exploratory project that you've not received a response from? If there is, please meet me after class. Simply because you should have some response. For the Kaggle thing, I feel like it's almost automatic whether you submit something on Kaggle or something on the on Canvas decides what grade you get for the proposal. But for exploratory, I would like to make sure that I actually give you some feedback. So if I missed responding to your proposal, let me know. Anyway, so you know what, we've spoken about this a lot. Are there any questions about the project proposal or the project intermediate status report? Yeah?
Going forward, how many more different submissions for Kaggle are we going to do?
So you will do 2 for this, right?
Yeah.
And then 4 more. So in all, by the end of the semester, I expect 6. And 6 does not mean, you can do, say, perceptron with learning rate 0.1 and perceptron with learning rate 0.2 count as the same submission. So 6 different algorithms. And a question came up, what counts as a different algorithm, because they kind of sort of start bleeding into each other. For the purposes of the project, every algorithm that has a different name is a different algorithm. The only exception could be margin perceptron and perceptron. I'm going to treat them as the same simply because they are so close to each other that I don't see how they will be different. Otherwise, for example, for your deadline on Thursday, you could do something like, say, perceptron and average perceptron. If you do that, you get 2 different runs. In your report, one thing I would like you to specify, I just realized this when I was going over over the Kaggle leaderboard last night. I would like you to specify which 2 runs you would like me to count as your official runs, because some of you have submitted dozens of them. So just so that I know. Okay? Other questions? Yeah?
Where do we submit the code? Sorry.
Oh, that's not for this report. That's not for this status. The code, you need to submit the code only for the final, only when the final thing is submitted. The report has to be submitted on Canvas, and of course the Kaggle runs are on Canvas. Yeah?
I have a kind of conceptual question about AdBoost.
Okay.
So I know that we have to use like heuristics that do better than chance. So like in our homework, it's like better than 50%.
Right.
What about in the case where like the data itself has like 95% positives?
So in that case, it has to be better than chance, whatever is the majority. So things get slightly more tricky with that. So you have to go, in some sense, the answer becomes clear when you look at the way that epsilon is used in the proof. Keep in mind that there is an implicit assumption in all of that theory that we developed for AdaBoost that chance is 50%. Otherwise, you'd have to reorganize, reweight things. There are multiple ways of doing that. One way could be to reweight the D's so that you still end up with 50% as being the threshold. Other questions? As I said earlier, there are a couple of talks that are interesting this week. There's one right after this class, and it's the third talk of the AI lecture series, and I think the last one of this calendar year. The speaker today is Rao Kambapati. He just goes by Rao. He is a distinguished researcher who's done a lot of stuff in AI. In particular, just as an advertisement, he was the last president of the Association for Advancement of AI. That's the premier AI research association. And he's going to talk about how AI interacts with humans and how we should design AI for interactive systems that and so on. It's right after, it's not next Tuesday. That serves me right for using last week's slide. Okay. So it's today, right after class. It's in this building on the third floor. If you don't have another class, I hope to see you up there. And the other talk that's interesting this week is Kiri Wagstaff from NASA JPL. She's going to talk about how machine learning gets used in space. Just as another advertisement for this talk, she's one of the coolest speakers I've met because she actually works with the Mars rover, and she actually works with spacecrafts that have gone to, they've gone farther than I travel every day. I don't know where, some Europa, it is something, I'm guessing Jupiter or something. Anyway, it goes to space. So she's going to talk about how we can use machine learning to kind of analyze data that's coming in from there. And she actually spends a day a week, at least until last year when I heard about it, a day a week working directly with the Mars rover team and testing. So this talk is at 11 on Friday. This Friday, not next Friday. So if you can make it, you should. It's going to be fun. All right. Another thing is Kiri is a Utah alum, so you should show up there to support. So we're going to get back to our usual programming. We looked at what Bayesian learning is, and the idea is that we assign probabilities to events and we treat everything as an event. A data set's an event. So it's the event that this particular data set among all possible data sets were available to you. A classifier is an event. The hypothesis is an event because it's the event that this particular hypothesis is the true one. And then we can design learning criteria under this worldview by asking what's the most probable hypothesis given that you have this data set in your hand. And using this, and the tool that powers everything that we'll use is the Bayes rule. The Bayes rule simply says that the posterior probability of some event given something else is proportional to the likelihood times the prior. And we'll keep using this all the time. Using this idea, we developed two different criteria for choosing hypotheses. One of them is called the maximum a posteriori criterion or MAP hypothesis. The MAP hypothesis is simply the one that has the maximum posterior probability. So the maximum value of P of H given D. But by Bayes' rule, we know that P of H given D is proportional to the likelihood, that's this term here, times the prior. And so the MAP hypothesis is the one that maximizes the product of the likelihood and the prior. Now, The prior is simply a way of saying, here is what I believe the classifier should be before you see any data. And the likelihood is asking, if this was the true classifier, what's the probability that this particular data set would have been generated? Now, sometimes, actually very often, turns out, we don't have anything intelligent to say about the prior. We don't have much to say about choosing one hypothesis over the other before we see any data, and in that case we'll use a uniform prior. Uniform prior is simply a statement that upfront, before I see any data, I know nothing, and I'm just going to believe the data. If you use a uniform prior, the second term p of h effectively becomes a constant, which means we can throw it out of the R max, and that gives us the maximum likelihood criterion. The maximum likelihood criterion picks a hypothesis using only the likelihood. It picks the hypothesis that maximizes the likelihood. The good news about all of this is that the names basically give you the method. Maximum a posteriori, I think, is Latin for maximum posterior probability distribution. I'm sure not, but you know what I mean. Maximum likelihood is English for maximum likelihood. So you know exactly what's going on here. Of course, you need to know what the likelihood and posterior probabilities are. In the last lecture, we instantiated this idea of maximum likelihood estimation on Bernoulli trials, where I went through this rather, what in hindsight seems to be obvious analysis of showing that when you have n coin tosses and m of them are heads, the probability of heads is m over n. It turns out that that is true because you're implicitly performing maximum likelihood estimation of the probability. Now, notice that I say maximum likelihood estimation of the probability, which means we are treating the probability as a random variable here, right? So the hypothesis in that case was the probability. And sometimes people feel a little uncomfortable when you're talking about the probability that some probability is something. You get used to it. So, are there any questions about all of the stuff that we've seen so far? If not, we're going to look at our next example of maximum likelihood estimation. My plan today is to work through this example and then see how far I can go with naive Bayes classification, where well, I don't want to give away the punchline. Let's go to the second example of maximum likelihood estimation. In maximum likelihood estimation, we want to find a hypothesis that maximizes the likelihood. Now, when I apply it to a new problem, so maximum likelihood estimation is just a general purpose tool that you can apply to any new problem. It's like saying I have a optimizer, I have a criterion for deciding what model to pick. But in order to actually use it, you need to give more information. You need to say what the problem is. The way you say what the problem is, in this case, is you need to specify what your hypothesis space is, what class of functions you are considering. In the previous case, the hypothesis space consisted of all probabilities. In this case, we'll get there later. You need to specify this. And the second thing you need to say is, suppose you knew that your hypothesis was little h. Then you need to show a way in which the data is generated. You need to have the probability that a certain data set is available. We need to get both these numbers, or we need to specify both these functions before we get started. Now, it turns out there's an interesting connection between maximum likelihood estimation and least squares regression. Remember least squares regression from way back? It turns out they are intimately connected, and we'll derive that. So, let's say the hypothesis consists of real valued functions. So the inputs are some d-dimensional vectors. The outputs are real numbers. Y is a real number. We're doing regression and classification. And our goal is to specify some set of functions such that the output is generated given the input. Now, here is what you probably, maybe for some of you, the first instance of what is called a generative story. A generative story is the story of the data. It's a formal specification of how we believe the data is generated. In this case, the generative story goes like this. Suppose an input is drawn. We don't care how. Let's say it's drawn uniformly at random. There is a true function, f. We don't know what the true function is, but the true function exists, and nature gets to label the example with the true function. So you get f of x. F of x is a real number. Now, nature being what it is, does not give us f of x directly. Before giving us that number, it adds some noise to it. It kind of just moves the point around. And how much does it move it around? It turns out, in this case, we assume that nature is kind enough that it does not move it arbitrarily. It moves it, or it perturbs it with a noise that is drawn according to a Gaussian distribution. And not just that, the Gaussian distribution has a zero mean. What that means is, so you've seen Gaussian distributions, right? I hope all of you have seen Gaussian. Now, what that means is the output y that we actually get to see, the data set that we have, consists of pairs x, y, which we are going to conjecture are generated this way. The x is drawn uniformly, and the yi is constructed by applying the true function and adding some noise to it. The noise is drawn from a zero mean Gaussian distribution. And this process was repeated m times to create the training set that we have. Does the story of the data make sense? There's no reason that this is how the data was generated. There's no reason that this is real, but it turns out it's going to be a convenient thing for us, so we will work with that. So we will have to, this is an assumption we are making. We're making this assumption that this is how the data set that we have is generated, and it's actually a very common assumption to make this, to have this sort of a Gaussian noise assumption for regression. So we have m examples of this kind. We can always ask, how good is my model? Now, we don't have f, of course, but we do have, we are entertaining the possibility that the hypothesis h is the function that generated, that is the true function. So we can always ask, what's the error of this hypothesis? The error is simply the absolute value, or we can even think of squared error if you want. It's the square of this difference. So the absolute value would be the absolute value of yi minus h of xi. The squared error is simply the square of that quantity. Now, let's think about this difference for a minute. If this particular h was really the true function, if h was the true function, so let me write down how we believe the data was generated. We believe that yi is f of x plus ei, f of xi plus ei, which means ei is, so we believe that the error is, this error is Gaussian. Now, if h that we are currently entertaining was really the true function, then that difference would also be Gaussian, right? Because if the data was really generated that way, then the difference is exactly that, and in that case, f is the true function, h is the true function. Now, if we believe that the error is Gaussian with a zero mean and some standard deviation sigma, we can compute the probability of observing a data point. It's simply the Gaussian. So it's the probability of observing a data point is the probability that the error is that particular difference. And this is the standard functional form of the Gaussian, the probability mass for a Gaussian. So far, questions before I fill up the slide with just math. Shall I move on? Okay. see one nodding head. I'm going to take that as a representative for the class. And so we have this probability that one particular example was generated according to our assumption. If h was a true function, then the example yi xi would have been generated. The probability of that particular example existing would be a Gaussian. Now, how did we get our data set? We got our data set by repeating this process m times. So, and importantly, the data set, every example is generated independently. Now, you will notice P of d given h is exactly the likelihood. P of d given h is essentially asking if h was the true hypothesis, what's the probability that this data set would exist? If all our assumptions are correct, then this is the probability that our data set would exist is exactly this quantity here. Any questions? Yes.
Since probability is lower than 1, and we're multiplying numbers lower than 1, wouldn't that mean if we see more examples, we get less probability of D and H?
Oh yeah, but that's not a big deal because you can't really, as you see more examples, you can't compare 100 example data set with a 10 example data set because one of them would be much different from the other in a different range. So that doesn't matter much. You compare 200 example data sets, and at that point, then the products will be equally large or equally small, depending on your perspective. But what you said, it turns out, has some interesting computational consequences. Probabilities get small. Probabilities are between 0 and 1, and you multiply them many, many times, and you'll get really small numbers very quickly. And it turns out that when you're implementing these things, it's always a good idea not to work with probabilities directly, but with log probabilities. If you work with probabilities directly, you will end up getting zeros and underflows very quickly because the floating point that we use can't represent those numbers. So we will almost never work with probabilities directly. We'll almost always work with log probabilities. In fact, I know some people who implemented their own libraries for Bayesian learning, and they've had to implement, the first thing they do is implement their own log probability library, and then build everything on top of that, simply because otherwise it becomes a nuisance to debug. But yes, just keep in mind that multiplying small numbers makes them smaller. Okay, so what we have here is the likelihood of the data is simply the product of all these Gaussians that we have. Our goal is to find the most likely hypothesis. So we're given a data set and we want to find the hypothesis that maximizes this likelihood. But we just derived this likelihood. In order to do that, we assumed a story about how the data is generated. We have the generative model. So here the word model is used in a slightly different sense. So I'll try to avoid doing it. That way we have the generative story. We have a story of how the data was generated. So we want to find the likelihood that maximizes this quantity. We can substitute that in because we just showed that it's a Gaussian. At that point, how do we maximize this? First of all, is this problem solvable? Assume that sigma is a constant. Let's assume that sigma is fixed. So, let's pretend that we don't really care right now. Can we solve this? How do we maximize this expression? Any ideas? Yeah?
Could you take the log and do something with gradient descent?
Okay, let's take the log and see what happens next. In fact, that's a good idea. Almost never you maximize likelihood directly. Almost always maximize log likelihood because log likelihoods are just nicer beasts to play with. So you take the log, and so the log of this quantity, we don't care, it just goes here. The log of, I'll just erase that. And the log of this quantity, log of e power anything, is that thing in the power. So that just goes here. So, and the nice thing about logs is that we no longer have a product, a huge product, but a huge sum. Now, first things first, taking the log is correct because log is an increasing function and we are maximizing, so all is good. The second thing is that what you said was a good idea or a good intuition. You should think of stochastic gradient descent or gradient descent, but especially stochastic gradient descent is a general tool for optimizing big summations. And if you can get your function to a form that looks like a big summation, you can actually then take advantage of those ideas that we've already seen. So that's a good insight. But we won't do that right now because we've already seen that a few times. Let's kind of move this a little, clean this up a bit first. Now, notice that this term here does not depend on h at all. It's a constant. So our max, that's just a nuisance that we don't need. So we're going to get rid of that. So we have something like this. So I just moved the negative outside. So we have this quantity here. So what does this look like? It's you add up the sum of all the errors, the squared errors, divide by this standard deviation, squared standard deviation, and you want to find a hypothesis that maximizes the negative of that. Maximizing the negative is the same as minimizing the positive. It depends on whether you're an optimist or a pessimist. So we can get rid of the negative and we minimize the sum of the squared errors. Oh, notice that I got rid of the sigma squared here, because that's also a constant. It's just multiplying everything, and when we are maximizing or minimizing this thing, it's just an extra constant that doesn't matter. Okay, any questions? Yes?
I want to know why the product tends to summation.
From here to here?
Yes.
Let's work that out. So, I'll write that at the bottom. So, I want to maximize. So, keep in mind, I want to solve argmax. Okay? So, argmax. Let's just pretend it's only two things. Okay? So that I don't write the whole thing. So, it is, let's say you have argmax of some f1 of x times f2 of x over x. It's exactly the same as argmax over x log of f1 of x times f2 of x. And this is true for, not f of f2 of x2. This is true for whether the product has two things or a million things. But log of a product is simply sum of the logs. So this is argmax over x log f1 of x plus log f2 of x, and this summation is really, if you run that along many times, you get this. Right? Other questions? So, yes.
What does it mean related to the standard deviation of estimates? Is that a realistic assumption?
Well, you want to talk about realistic. What part of what we did was realistic? I don't know. I mean, it's a convenient assumption. It turns out it just makes life a little bit simpler, just ever so slightly simpler. You could have dropped that assumption and thrown that into the maximization as well. And you maximize over that quantity also. It wouldn't have hurt too much. I just did that mostly because it's simpler, and it also gels well with the next point I'm going to make. But you could have assumed, you could have dropped that assumption and hoped that you can find the best standard deviations. Because at that point, what will happen is your maximization will no longer just be about h, but also over sigma. So you'll have all over the place. Alternatively, you could pretend that your sigma is part of the hypothesis. Your hypothesis has one more parameter, sigma, which you do your maximization over. So I agree that it's not an assumption that seems particularly sound, but it's an assumption that is convenient. And if you another answer to that same question could have been, it's a hyperparameter. You do cross validation, you find the best sigma. Increasingly, you will see that you will have all these magic constants thrown around, and whenever you're asked what is the value of that constant, you will be told it's a hyperparameter. And you do cross validation to find the best value of that, for example. So you could have done both. Okay, so what we have now is that the maximum likelihood hypothesis through this whole derivation is exactly the same as the hypothesis that minimizes this sum of squared errors. Now, notice that I still haven't made any assumption about what h might look like. It's still something that we can choose. I could choose h of x is maybe something that involves sinusoids. I could do whatever I want. It's a hypothesis choice. It's the same as the hypothesis choice that we've always made. We could, for example, consider that the hypothesis space that we are working with is the sum of all linear regressors. So h of xi is simply some weight w transpose xi. At that point, I can just plug that in, and you get this h of x gets replaced with w transpose xi, and what you get is the maximum likelihood hypothesis is the same hypothesis. So at this point, I write HML, but I could have as well written WML because the W completely defines the hypothesis. So at this point, the hypothesis is the set of weights. Every function h is defined by the W. So the weights are simply the ones that minimize the sum of the squared errors. You've seen this before, right? This is exactly the same as least mean squares. In fact, if you were a Bayesian, we did least mean squares all wrong in the beginning when we first saw it. It was just arbitrary. Why do you care about minimizing squared error? If you're a Bayesian, you care about minimizing squared error because it comes from the term in the power in the Gaussian. This is the Bayesian explanation for least mean square regression. So there are a whole series of assumptions that are in place to make these things align, but this is a general pattern that we will see quite often. You can arrive at a certain classifier, at a certain way of generating learning classifiers through this perspective of loss minimization, where you say upfront, I don't know anything about probabilities. I know what an error is. I consider a classifier to have made an error if the value of this y minus w transpose x is very large. That seems fine. So I'm going to define an error as the squared difference. And I don't care about probabilities and stuff. All I care about is just minimizing this loss, minimizing the difference, the squared difference, and that gives us the loss minimization perspective for the least mean squares. Alternatively, I could be Bayesian about it. I could say, oh, there's no such thing called a loss or anything. What I believe is that the data is generated this way. There's a generated story where the errors are Gaussian. And not just that, the errors are Gaussian over a linear function. So there is a normal distribution that generates the errors, and the true function is linear. And I'm going to learn the true linear function using maximum likelihood. You kind of run with that idea, follow it all the way to the end, and amazingly you end up with exactly the same objective. I don't know about you, but I find this to be extremely satisfying. You have two extremely different worldviews that converge to the same criterion for learning. And maybe that says something about its underlying correctness. You have two ways of getting to the same answer. Any questions? About these two perspectives or about the derivation itself?
I have a question.
Mhm.
So I don't know if you know the answer to this, but were the two ways of thinking about this discovered independently and then like later found out to be the same, or did they rely on each other to like come
It's
up?
really hard to tell actually. It's hard to tell who's influenced by whom. Maximum likelihood estimation is more than a century old, at least the way we see it now, the way the formal definition. Loss minimization has had a somewhat independent lineage, but who knows who talked to whom. So I don't know. I would like to think they were independent, because that makes it a more, the story becomes more nice. But
Can you go back to the slide when you had the sigmas there?
which tell me when to stop.
That one. Yeah. So maximum likelihood estimators, they don't. We can drop the sigma safely if our hypothesis doesn't depend on sigma, right? Because
Oh, you mean big sigmas? Sorry, the denominator, not the big sigmas. Okay. Yeah.
Right. So it's like I think it's kind of safe to drop it because as
Oh,
long
yeah.
as we don't assume the
Right.
variance is part of our hypothesis.
Yes, that's right. That's why I said if you assume that the variance is part of the hypothesis, then you can't drop it. Right. So if your or instead of thinking of it this way, if your maximization is over sigma as well, you can't drop it. If your maximization is over sigma, then notice that this is kind of an annoying problem to solve because you have a sum of some fractions. It's a little bit ugly, but yeah, you're absolutely right. If you're a more mathematically concrete way of putting that is, if your maximization does not involve the sigmas, then you can drop it. Whether you consider sigma as part of the hypothesis or not has nothing to do with it. If you consider your sigma as part of the hypothesis, then it automatically becomes the maximized over. But you could pretend that sigma is not part of the hypothesis, but still you maximize over it. But really, if you had a sigma here, you can't drop it. So yeah, and one of the reasons why you tend to treat this as a hyperparameter rather than optimizing over it is because it's a slightly more painful thing to optimize. Or instead you could, it's a constant. You pull it out, and you could do things. Yeah, it's not the worst thing to do. I take back what I said. Yeah.
I'm having a hard time finding connection between this and what we learned last time. From my understanding from last time, we were looking at the probability of finding the true function if I have a specific training set
Yes.
and a hypothesis.
Yes.
What does this one give?
This one gives you the same thing. So remember how we started this whole thing. We want to maximize the likelihood. So this quantity here is probability. It's the likelihood of the data. So this is exactly the same as the same thing that we worked with in the last lecture. It just so happens that it's not. In most cases, you never stop with that. You have to instantiate a specific probability distribution and work out the details of the optimization to get the function to a form that you can solve. So the connection is through the actual process that we just went through.
So what? I think I need to go through.
So no, go ahead.
This one is telling me that in best case scenario, the likelihood of finding the true function using H is HML. Is that?
No. Yeah, so I use Argmax here because it makes the equalities valid, but HML is the true function, is the best function according to this criteria. So think of it this way, okay? even higher level than what we saw in the last lecture. We have some, so H best equals it's just defined to be the best classifier according to some criteria. Now, we can define different criteria. We can say the criterion for defining the word best is the one that minimizes loss. We could say the criterion for defining best is the one that maximizes likelihood. So, under the Bayesian perspective, there are two standard criteria for defining best. There is MAP and ML. We are working through what happens if we use the maximum likelihood method. So we are just asking, so HML there is the best classifier according to the maximum likelihood criteria. And so we, in order to follow through with that, then we have to actually write down what's the likelihood of the data. And once we write down what the likelihood of the data is, the whole thing just falls. The starting point ends up being essentially the same for many different Bayesian learning methods, where you define the best function is the one that maximizes, say, the posterior probability or the likelihood. So you write down one of these things, and then you kind of make assumptions about how the data is generated, and you have to follow through. Oh. Yes. Okay. So what we have here is two perspectives about linear regression, and sometime maybe next week we will see a similar sort of thing about logistic regression, it turns out. But we'll get there when we get there. So just to summarize what we have seen so far with Bayesian learning, it's another way of asking what's the best hypothesis for a data set. If you're Bayesian, there are only two right ways of answering that question. Either you can be doing, or there are two of the best right ways of answering that question are by using maximum likelihood or ML or maximum a posteriori or MAP estimation. What we actually saw is something more specific. It's not enough to say that you're using maximum likelihood estimation. If you're using maximum likelihood estimation, invariably you have to actually work out the details of the estimator to see how, to show how the classifier is actually learned. You invariably have to set up an optimization problem. What we saw was we saw two versions of this thing. In the case of the Bernoulli trials, of the binomial distribution, the optimization problem was really not an optimization problem. You could have taken, it was calculus 101. You take the derivative and set it to 0, you could solve it in closed form. For regression, it turns out you could also solve it in closed form, but as you pointed out, you could have used gradient descent. So sometimes you can solve, once you write down the likelihood expression, or the log likelihood usually, it's not enough to stop there. You need to work out the details of the optimization in terms of your hypothesis, and sometimes in some very nice cases you might be able to solve it in closed form and just get an answer. And in some cases you can't get an answer and you need to use an algorithmic approach. And invariably those algorithms could end up looking like stochastic gradient descent. What you will also, what you should be comfortable with is you should be able to apply these two ideas for simple problems. So I could give you a generative model saying that, assume that the data is generated using this sort of a criteria, in this fashion. The probability of generating an example is this thing. Now you should be able to write down what the likelihood of data set is. You should be able to maximize that thing and come up with the best classifier. And we'll see at least two more examples of map, at least one example of MLE and one example of map. Questions before we switch tracks? Okay, switching tracks. We're going to look at the naive based classifier. How many people have heard of the naive based classifier? How many people have seen it before or used it or implemented one? Okay, the hope is that at the end of maybe today and tomorrow, the next lecture, you'll be able to implement it, and not only will you be able to implement it, you'll realize it's one of the easiest things to implement. So the plan is we will see what the naive Bayes classifier actually is and why it is the naive, what's the naive Bayes assumption. And most likely we won't get to the learning part today, but we'll see how to learn the naive Bayes classifier using, once again, the maximum likelihood criterion. And there are some practical issues that we'll have to consider. So let's look at what the naive Bayes classifier is. Before we get into the details of the classification of the model itself, I just wanted to mention this one confusion that people will have maybe about 15 minutes from now, which is, we've seen Bayesian learning. Bayesian learning is a probabilistic criterion for picking what the classifier is given the data set. And we have seen, what's maximum posteriori and maximum likelihood estimation. You should know what the difference is between them. I'm not going to, ask that question. You should know what it is. If you don't know what it is, let me tell you what it is. Maximum posteriori or maximum likelihood assumes that you have uniform priors over all hypotheses. But it turns out we could, also learn functions that predict probabilities. So we could learn functions that predict what is the probability that this email is spam, for example. Instead of actually predicting the value itself, we could just learn a function that predicts the probability. And then afterwards, we can decide whether it's spam or not by thresholding it at half. If the probability that this email is spam is more than half, then we call it spam. Otherwise, we call it not spam. So we could learn classifiers that predict probabilities. Now, the cool thing is, once we have a classifier that predicts probability, we can use what is called mapped prediction. We can be Bayesian not just about the learning, but also about the prediction. We can ask what is the most likely label for this particular example. So this is different from map learning. Map prediction essentially uses the Bayes rule for predicting a label for a given example. So we want, under this scheme, we want to know what's the label, what's the probability of a certain label given an example. Keep in mind, at this point, we're not asking what's the label, we're asking what's the probability that the label is something, which is different. And given that if we have an example X, the probability of a label being Y is, this is just a conditional probability. We can apply Bayes rule, and this is exactly the same as the probability that the label is Y up front, the prior probability of the label being Y, times the probability that if the label is Y, what's the probability that we generate, the example X is the one that exists, divided by the probability that examples exist. If we had to do this, then we can, if we had something like this, we could easily convert it into a decision rule. The decision rule would simply say, my label is whatever maximizes the posterior probability. This is also a posterior probability. This is the posterior probability of a label conditioned on an example. So I could ask, what's the which of my labels maximizes the posterior probability? At this point, notice that so far, nothing in what I said assumes that we have a binary classification problem. You could have an infinite number of labels. You could have 18 labels. It doesn't matter. The math is right. So you could always ask, what's the label that maximizes the probability? But that's exactly the same as the label that maximizes this expression here. That goes here. But notice that this maximization is only over the labels. Right? So what can we do? it's structurally identical to what we did for map learning. The denominator does not depend on y. When we are entertaining the possibility that label 1 and label 17, when we are comparing label 1 versus label 17, the denominator p of x equals x is a constant. It doesn't matter, so when we don't need to even do the division, we don't even need to calculate that value. So instead of keeping this denominator, we can just throw it out. So we can predict the label for an example using this criterion here, which is the probability of generating the prior probability of the label times the probability that we generate this example using y. At this point, at least one of you is confused. The big confusion that I found happens is confusing with map learning. In map learning, we are being Bayesian about the learning process. In map prediction, we are being Bayesian about the prediction. In map learning, the random variables involved are data sets and hypotheses. In map prediction, the random variables are instances and labels. This is just prediction. It just so happens that basically the same math works in both places because the Bayes rule is correct for all probability distributions. So this is what I meant in the last lecture when I said you could be Bayesian about other things. You could be Bayesian about prediction, you could be Bayesian about learning, and it turns out these two things wonderfully interact with each other when we come to naive Bayes. Any questions before we? Before we move on, actually, are there questions about this difference? In this case, we are assuming that our hypothesis space consists of probabilities. Our hypotheses are defined by probabilities because somewhere inside this, if you want to find a value for y given x, you need to calculate this thing and you need to calculate this thing, which should be somehow contained in our hypothesis. So our hypothesis consists of probabilities. So our concepts that we are learning are now probabilistic concepts. Once we have that, we can do map prediction. Questions? Yeah?
Why are we maximizing over y?
Can you complete the sentence as opposed to?
I don't know.
Okay.
I just
So-
started jumping.
Yeah, so let me. So let's say we have trained the classifier. Okay. What does it mean that we have a classifier? It means that we have these two probabilities. We have whatever those functions might be. At this point, we are making no commitments as to what those functions might be. We have some functions. Now, this learning was done yesterday, and it's frozen. We have those functions. Today, I give you a new example. All I care about is the label for that example. That example is x. That example is x here. And my goal is, I don't care about other things. I only want the best y for that example. In order to do that, I'm going to enumerate all possible y's that exist. If it's binary classification, it's just two things. And find the one that's best. Specifically, under map prediction, we define the best label as the one that maximizes the posterior. But working through this whole thing here, maximizing, given this particular x, I want to find the best y, using a classifier that has been learned and frozen, that is map prediction. And that's exactly the same as maximizing this one. That's why we maximize over y. Yes, and this is where the confusion starts, right? Everywhere until now we were maximizing over h. Now suddenly we are maximizing over y. It turns out this perspective is useful for generalizing beyond binary classification because in general we want to consider all possible labels and find the best one. Just like we want to consider all possible hypotheses during learning and find the best one, at prediction we are considering all possible labels for an example and finding the best one. Once again, we have to define what best is. Yes? And how do we define best? If we are Bayesian, we don't have to think about it. Best is maximum a posteriori. So if at prediction time, the best label is the label that has the highest posterior probability. At learning time, the best classifier is the classifier that has the highest posterior probability.
So what does it mean to have the highest?
So what it means is that we have these, until now, pretty much all classifiers that we saw assign some scores to examples, right? You take let's take something like a linear model. You take a example, you compute a dot product, and you look at the score. Let's call that the score. You look at the score. If the score is more than 0, you call it positive. If the score is less than 0, you call it negative. Alternatively, let me just define a different scoring function. And this is not for, it's not directly related to Bayesian stuff, so let me move the new page. So let's say we have given example x and weight w. I define the score of label equals plus 1 to be w transpose x, and the score of I could define it. I'm just making what might seem like an arbitrary choice. At this point, I can say prediction is find the label with the highest score. Now, let's consider the cases. If W transpose X is more than negative W transpose X, then I pick positive. If that is label is plus if score of plus is greater than of minus, right? And label is minus if so first does this, I mean, trust me when I say there is a point to this. Okay? I could do this. But now what is, let's just expand on these things. This means label is plus if how did we define score of plus? Is W transpose X is greater than the negative W transpose X. Or if 2 W transpose X is greater than 0, which means if W transpose X is positive, you can put it greater than equal to if that makes you feel better tonight. Right? So, effectively, by defining the score this way, we come back to the decision rule we had. If the sign of W transpose X is positive, then the label is positive. Effectively, that means we could have defined the prediction problem this way. We have 2 labels here. Maybe I have 18 labels. Or maybe I have exponentially large number of labels. For every label, I use my classifier to produce a score. And we find the label that has the highest score. Now, some scoring functions, my hypothesis choice is basically the scoring function. Now, it turns out that some kinds of scoring functions are nice in some sense because they come with extra properties. One big family of them are probabilities. I could define the score of positive using the probability of it being positive. It's just a function. Probabilities are just functions, right? Instead of doing this, I could have defined the score of plus as probability of plus given x, and the score of minus is the probability of minus given x. The whole thing, the argument follows except for what's in the box. Because at this point we have specifically done this here. I could have done that, but that means that we need some way of writing down probabilities. Probabilities are also functions. They are functions that are equipped with extra rules about how to modify them, and that gives us some tools to play with. So we need to make assumptions about the probabilities, the functional form of the probabilities, instead of the the linear model or whatever. So when we are learning probabilistic concepts, we have to make assumptions. We have to treat probabilities as functions and make assumptions about the probabilistic form. Now, the nice thing is, if the true label, if the scores were defined to be these probabilities, these are, by the way, posterior probabilities. If the scores were defined to be posterior probabilities, finding a label with the highest score is exactly the same as map prediction. It's exactly the same as finding the label that has the highest posterior probability or maximum posterior probability or map. So map prediction requires that you score every outcome with a probability, or you have some mechanism of computing the posterior probability and you want to find maximum. I have not told you anything about how these probabilities come into existence. That is, we need to make some assumption about the functional form of these things, because we need to somehow learn them. We can't just say probabilities. We need some function that we can actually optimize over. At this point, I just want to introduce the idea of map prediction. We still need to assume how these probabilities are going to show up, and that's going to be a big part of the naive Bayes assumption. Does that answer your question? Okay, so that's about map prediction. The nice thing about map prediction is we can play the same game that we did with any maximum or posteriori objective. We have two parts to this prediction. We have the likelihood and we have the prior. In this case, the prior is the probability of y. What does that mean? It's the probability that the label is y before you even observe the example. If, for example, you did not have any information about the specific example that you need to classify, but you have a hunch that positive labels are extremely common, the prior could capture that. Usually it's not a hunch, usually it's learned from data. The likelihood is the probability that if the label is y, the probability that example x that you currently see, it would be generated. Is the likelihood of observing this example conditioned on the fact that the label is some y. So, as I said earlier, in order to use map prediction, one way of using it is to say, if only I had these two functions. These are functions. These are really functions of, one of them is a function over x, the other one is a function over y. If only we had these two functions, I could just make this prediction. So let's learn those functions. We need to estimate these functions from data. We need to get some way of discovering these two probabilities from data, and we are going to be Bayesian about that again. We'll get there in a minute. Yes?
So, the likelihood function doesn't have anything to do with the dimension of
The what?
doesn't have anything to do with dimension of x. Because then
It does. It does. Can't end your sentence because that's a good observation.
okay, because then I was thinking if you have like a big data set with a big feature and then that thing tends to zero.
Hold on to that thought. That's literally what I'm going to say next. Not exactly quite that, but it doesn't matter if it tends to zero because you're comparing only over the y. So it doesn't matter if you have small numbers. They will kind of be in the same numeric range. But if you have a huge dimensional data set, things are going to be problematic in a different way. Always be concerned when the dimensionality is large. In general, that's like one of the important lessons of the machine learning class is to have a healthy fear of large dimensions. Let's play tennis again to kind of illustrate all of these things. We've seen this before when maybe in the second week of class, the task is to decide whether we should play tennis or not based on some observations. We need to, in order to use the maximum, this style of map prediction, we need two things. We need the prior and the likelihood. The prior looks like, is basically a table that may look like this. What's the probability that you play tennis, and what's the probability that you shouldn't play tennis without any other information. Before you know any other thing, it says here that it's more likely than not that I won't be playing tennis because points up. And also, in order to, so as a matter of efficiency, this may seem like a silly point, but as a matter of efficiency, I really need to only know one of these numbers because the other one is 1 minus that. So in terms of memory that's needed, it's just one number. The likelihood consists of a lot more numbers. It consists in this case because we have binary classification. So the likelihood is really a term that looks like P of x given y. Given y means you have to consider both cases when y is yes and y is no. The probability of the temperature and the wind, given that tennis is yes, is one part of one table and this is another table. These are just conditional probability tables. The top part says, on days that I do play tennis, what's the probability that the temperature is something and the wind is something else? The bottom part says, on days that I don't play tennis, what's the probability that the temperature is something and the wind is something else? So, how many numbers do I need to store this table? Notice that these four things add up to 1, and these four things add up to 1. So really I need to store 3 numbers here, and this is just 1. So with 7 numbers, I have the mod. This was the function, the probability function that we need in order to make map predictions. Now let's actually make a map prediction and work through the process. Suppose on a certain day, first of all, let's say you have estimated this table. You've estimated this table by looking at a lot of data and you are fairly confident that this is a good estimate. Now, let's say today you have to decide whether you have to play tennis or not. So you take measurements, you observe that the temperature is hot and the wind is weak. So H and W. So should you play tennis or not? To answer this, you need to solve, compute the value of the likelihood times the prior. The likelihood is P of H, W given play, and the prior is probability of play. And this argmax is really over y of play taking the value yes or no. When the output is when the label is y, so when label is yes, you can look up this value in the table. So let's see where that is. This row here times here is this. So it is 0.4 times 0.7, 3, that's 0.12. When it's no, it's this row here times this quantity, so it's 0.07. So the product on top is higher, so you're going to play tennis. Essentially, if you want to compute the, so the map prediction here is yes. If you want to compute the probability of yes given H, W, it's really probability of H, W given yes. Let me zoom in. I want to compute probability of yes given we have the first, important thing is note that we only have the numerator. The numerator is this number 0.12, and if you want to actually compute the probability, you just have to normalize these two things. So it is 0.12, and it's just something that you should keep in mind. That what we have is not the probability, but just the product of the likelihood and the prior. Yes?
So could we derive something like that likelihood table from the training data, or is this working under the assumption that the likelihood table is just given to us?
For now, we're going to assume that the likelihood table is given to us. But literally the next thing I'm going to say is how hard is it to learn that table? But before, and we will see a very deep connection to the dimensionality there. Before we move on, any questions about what we discussed here? This is an example of maximum likelihood prediction given, a maximum a posteriori prediction given the likelihood table and the priors. Now, the likelihood here is a table, but it doesn't have to be a table. It could be a function. It could be a function that generates the probability. Right? All we need is something that gives us this value. You could parameterize it as some function. Questions? So if you've not seen this before, this is a lot of information we are covering today. So I would want you to go back and revisit these things. If you've not seen this before, also this style of thinking could be a little disconcerting because we're essentially, it seems like we're using the same trick again and again. We keep throwing the Bayes rule at something and every time we get something else. We do learning, we do prediction. But there is some method to this madness and I want you to kind of mentally arrange these concepts in your head. But yes?
I'm thinking about how realistic is this because I'm finding a problem if in real life I'm going to predict the likelihood of something based on do I know that only these features can fit the output?
Now, so let me rephrase that question because I think that's a very insightful point. So the question was, this totally seems bogus. Temperature and wind don't depend on whether I play tennis or not. It seems kind of twisted. Moreover, maybe there's something else that decides whether I play tennis or not. Maybe maybe I have class, I can't play tennis. And that's not even in this table. So how could this possibly be realistic? It turns out we've been living this life since the beginning of the semester. We just call them features. We call them features and we said, yeah, these features are enough to make a prediction. Who's going to give you the features? Oh, you think hard about it and you come up with the best features you want. We always make it somebody else's problem. But this is one of the nice things about what we are doing right now is that it exposes that assumption. It brings it to the front. It makes the ridiculous stuff stand up. It makes it look like, on days that I decide to play tennis, the temperature decides to be cold. Right? Because I'm asking what's the probability that it's cold and there's no wind on days that I decide to play tennis. So the causality seems inverted and it ignores other possible columns that the table could have. And these two things come to the front in this viewpoint, from this perspective. But we always have that. When we use perceptron, somebody gives you features. How do we know that these features are relevant? When we used decision trees, how do you know that these are the features? We pretend that, maybe we don't have all the features, but we could transform the features to do something. But the information that you have is what you have. Alright. We still have only 3 minutes, so I just want to kind of seed this idea and then pick up on this in the next lecture. Let's say we have this full table. And the question that came up is, how are we going to get these probability tables? How are we going to learn these numbers? And there were hints about the answer to this earlier, about the difficulty of it. So let's say we have this full data set of 14 examples. This was the same data that we used in the decision tree lecture. What do we need to learn? We need to learn these two tables. We need to learn the prior and the likelihood. The prior is always, in binary classification, the prior is just a single number because you just need the probability of plus. And the probability of minus is 1 minus that. Let's count how many numbers we need for the likelihood. How big should that table be? So there are 4 features, which means that for play equals plus and for play equals minus, we need an assignment to this row in the table. So this is, when play is plus, this would have been the row at the top half of the slide, and when play was minus, this would have been a row in the bottom half of the slide. So we need an assignment for each of these things. How many such assignments can exist? So this particular column, this column here, takes 3 values, this one takes 3 values, this one takes 3, and this one takes 2. So if I enumerate all possible x1, x2, x3, x4, all values of the features, how many combinations exist? Who did the math so fast?
Well, 54, and then you have.
How do you multiply so fast? But yes, I didn't even bother. It's 3 times 3 times 3 times 2. It's all possible combinations of these, minus 1 of course, because we don't need the entire table. We add them up, we have that one thing, but that's not saying much. And we need those many numbers for play equals plus, and we need those many numbers for play equals minus, and that's, I believe you, it's 108, minus 2 actually, 106. We need to store 106 numbers if you have 4 features. Instead, if you have k labels, let's say, the prior consists of k minus 1 values, because 1 for each possible y. The likelihood, if your features are all Boolean, you will have 2 power d, because every feature can take 2 values, and there are d features, 2 power d minus 1 times k parameters. Once you see an exponent in the dimensionality, you know you've lost again, because that's too many. And we don't, the dimensionality depends on features, and we don't know what features are good. We're going to keep throwing features at the problem. So I'm going to stop with this. If we are not careful about how we think about the problem, we might end up having to learn these likelihood tables that are massive. And what I would like you to think about before you come on Thursday is how do we solve this problem? And I actually want you to think about it without actually seeing the answer that's literally on the next slide. It's an interesting question, and it turns out many people come to the same answer independently, so I want you to think about it. I have home class at 4 o'clock. Remember that you have homework due today, and also please come to the talk if you can.